Okay everybody, I'm gonna go over an example today. It's a seamless supported beam. I'm gonna design the reinforcement because the cross section, there will be a limitation on the cross section to use 10 inch by 16 inch overall depth. So I'm gonna be designing the required steel for that, flexural steel. Then the most important thing about this example, I'm just wanna show you how we calculate the deflection or how we check the deflection and the crack control criteria. And if I have some time, I may also touch base with the development length and cutoff points. So a cross section, a rectangular cross section is given to you, which is 10 inch by 16 inch. And the beam is seamlessly supported beam, and it has a dead load of 1 kip per foot and a live load of 0.75 kip per foot. Both are service loads. Fy is 60 ksi, F'C is 5 ksi, and cover equal 2 inch to the center of the steel. So if we calculate the ultimate load, W ultimate equal 1.2 times the dead load, which is 1, plus 1.6 times the live load, which is 175. So you will have W ultimate equal 2.4 kip per foot. Now M ultimate equal W ultimate L square over 8 equal 2.4 times 24 square over 8. So your M ultimate is
172.
172.8
So 172.
kip foot. Okay. So the maximum width is 10 inch, that's allowed to us B, and H is 16. So if H is 16 and the cover is 2 inch, so D will be 14. So we have B equal 10 and D equal 14 inch. What we need to do now is to calculate the required amount of steel. We have the following formula. If we use the design aid, the easiest, M ultimate equal phi R B D squared. So from there everything is given to you except R. Once you find R, you can calculate rho, and you can find rho, and I'm going to show you how. Then from rho we can calculate the area of steel. So this is the moment 172.8. This is in kip foot. So I'm going to change it to pound inch. So I multiply by 1000 to change the kip to pound and 12 to change the foot to inch. So it's going to be multiplied by 12,000 equal 0.9. This is the phi factor, and we're going to check it. R times B is 10 and D is 14. So 10 times 14 square. If you do this, you will calculate R equal
1175.
1175. Are you sure? So 1175, and the unit here is PSI. If you go to the design aids, that is R. That is R, which is basically the factor of the moment. Okay. So our Fy is 60 ksi. Our F prime C is 5000 psi or 5 ksi. So we need these are the R values. We are looking for an R value of 1175. This is where I am. Nothing in here. So I'm almost there. Then I have this value in here. So there where I am, I need 1175, which is almost the maximum, which is in between those two numbers, very close to 1196. So I go horizontal, I calculate row needed is between 0.023 and 0.022. So I'm gonna pick 0.023. So row approximately 0.023. Now I have to be careful. I need to go back and check this row against row max and row 0.005. Row that ensure the strain in the steel will be 0.005. Why we are looking for that row? Because the phi factor will be 0.9, and my calculation here is based on the phi factor equal 0.9. If this row that I am picking is less than row 0.005, I will be fine. My calculation is good. So I go there also, I calculate row 0.005 is 0.0213. 0.0213. So row 0.005 equal 0.021. Now look, to design this section as singly reinforced beam, I need row more than row 0.005. It means the phi factor will be less than 0.9, and that's what I know. This is the maximum steel that I can use as a singly. That will give you the maximum moment I can use. I'm still allowed to use more than that by the code. I can go up to row max. However, as you go with the steel now, you are decreasing the phi factor. You are gaining nothing almost. So in other words, you can say this design cannot be done as singly. We have to help with doubly. So row 0.005, the maximum I can use is, let's say, this number, or I can try row max to show you. I'm going to show you now. So if I use row 0.005, which is this value for f prime c equal 5 ksi. So this is ultimate. We need to provide phi mn greater or equal this number. Let me show you now. So for row equal 0.0213, the R is from that chart, the same chart, 0.021, R is 1073. And we know the phi factor for this one is 0.9. So this one will give you phi mn equal 0.9 times R, 1073, times B, you have it 10, times D is 14 square. If you do this, you divide everything here by 12,000 to get it in foot kip, your answer will be 157.73 foot, which is less than or equal ultimate. No good. Now let me someone will try go with row max. That's row max. When the strain in the steel is row max, the strain in the steel will be 0.004. That's the maximum you can put. That's the maximum the ACI code allows you to do. And row max equal, can be calculated by. There is equation to calculate all of that. We went on all of these calculations. We explained it really well. But rho max for that is 0.0243. And R for that, I think is the maximum we have in that table, which is 1196. R 1109. But the V factor, we don't know. You will see. You will see. The V factor will not be 0.9. It will be less. So Mn equal 1196 times 10 times 14 squared. You divide by 12,000 to get it in cubic foot.
195.
195 cubic foot. This still need to be multiplied by the V factor. If the V factor was 0.9 and you multiply by 196, you will be good. How much you get?
175.
You get 175. But the V factor is not 0.9. I'm going to show you how we calculate the V factor now. We calculate the V factor from the strain distribution. How much the strain here in the steel? How much the strain in the steel will be for rho max? It's given to you. It's 0.004. So the formula I gave you before for the V factor, I think it's 0.48 plus 83 times epsilon T, something like that, which is the tension, the strain in the tension steel. If that number here is 0.004 times 83 plus 0.48,
it's 0.812.
so it's 0.812. So how much VMN now?
158.
158 cubic foot. Now just watch. Just watch this. So you are using more steel, which is 0.0243. That's a lot more than that. You are getting the same strength. You are getting the same strength according to the ACI code. However, if you take both beams to the lab and test them, this will give you higher strength than the other. But based on reliability and safety things, safety considerations according to the ACI code, that's how they impose the V factor. So if you are following the ACI code design, and most of code designs, they give you the same strength. In real life, this is stronger than that. But when you talk about strength, you including the V factor, this is stronger. So that's a good demonstration. Basically, you need to design this one as doubly now. You need to help with doubly or negative steel, if we want to go with that. Or you can change the dimensions. Or if you are allowed to change, like the width B would be sometimes flexible with that. The depth you may have problem with that. You may have problem with that. So if we are flexible to change the width a little bit, I don't want to go solve this one into doubly, because the reason behind solving this one is the deflection calculation. So I'm going to assume now, or change my assumption, that I can change B. I'm not allowed to change the depth. I can change the width. Let's see how much B that will help me, that the design will be okay. I don't have to design this one as doubly. So we said ultimate is how much?
173.
Almost 173. Approximately 173 cubic foot. So look, I'm gonna use rho 1005, which is 1021. If we use this rho, we said how much our R will be. We just went through the calculation, or from the table we get it.
1073.
1073. Now just put these together. So 173 times 12,000 to change it to inch pound equal, the phi factor will be 0.9 times R is there. This is in PSI, by the way, from the table. Times B, you want how much? This is what we want. Times 14 square, because this is fixed. So for this to occur, B must be
10.96, almost 11.
almost 11 inch. I need at least 11 inch. So that's our section. We will change this one to 11 inch. If you want to go with 12, that's fine, but let's change it to 11 inch. So now the section with this area of steel, he will give me exactly what I want. So now my B is 11, D is that. So what's area of steel now? The actual area of steel is rho, which is 0.021 times 11 times 14. So the area of steel is
3.23.
3.23 inch square. That's how much positive steel you need. And the beam is designed as singly. So you go to the table, the first table, the steel table. So you see how many, you're looking for 3.23. 3.23. We're looking for a combination of how many bars of any size that will give me that number, like 3.23. So try to keep the number to 4. So you know what, since I increased a little bit, so look, if I use 4 number 8, they will give me 316. So I'm going to use 4 number 8. Use 4 number 8. That will give you AS equal 3.16 inch square. I'm fine here. I'm so close here. Why? Because I rounded up this one up to 11. Now you can be safer if you put this one 12 inch, then for sure your design will be more than what you need. If we have this one to be 12 inch. Okay? But now you'll be so close, almost the same. Okay? So let's say that's what we have. 4 number 8. Our bars will be 4 number 8. For number 8. That will give you exactly the same design strength VMN will be almost the same as MU. Okay, if you calculate the actual MU, which is 172.8. Okay. So usually, if I want to ask you something about the deflection by itself, check the deflection. I will give you the steel there. I will give you all the design. I will tell you check the deflection. Is the deflection okay or not? Look, there is a table in the specified by the ACI code, and it's available in every concrete design book. Shows that or tells you the following for slabs, ribbed slab, or beams. If the beam overall depth is less or equal this value, the deflection doesn't need to be checked. Okay, the deflection doesn't need to be checked. So let's see this table. And in most of these books, you know, deflection is chapter 7. So that table I'm referring to for our class is 7.1. Says for simply supported beam, for deflection not to be checked in beams, the depth must be at least L over 16. If H is less than or equal L over 16, deflection is okay. Let's see what's L over 16. So this equal 24 times 12 over 16 to have it in inch. So if H is this or equal, how much?
18.
18 inch? No. Our H is 16. No. 16 is less or equal than 18, deflection must be checked. Deflection must be checked. Okay, so we need to calculate the deflection and evaluate that with the ACI code requirement. For let's say we're going to evaluate the immediate deflection due to the live load. The immediate deflection due to the live load. But this, before we calculate the deflection, as you guys know, the formula for the deflection is the following. The formula for the deflection is the following. Delta max for assembly supported beam equal 5W L to the power 4 over 384 EI. We're talking about concrete, so E concrete. E equal 57,000 square root of 5,000. EC, this is EC. And this is I effective. So EC equal square root of 5,000 times 57,000.
The big number is 403 30508. Not 05 now.
If you divide by 1,000 to get in KSI.
Oh, then just 05. It's 40,305.
4,000?
40,000.
40?
4,000. You're right.
Like this?
Yeah, no, 4,000.
4,000 times, what's after? 40?
Oh, 4030.
30.
Yeah, there we go.
This is KSI. This is KSI. And I have, if I'm asking about the dead load, or the live load, sorry, I have W and I have the length, it's given to me here. The only thing I need to calculate is I effective. And the formula for I effective is, okay, we said M cracking over MA cube times I gross plus 1 minus this thing here, 1 minus M cracking over MA cube times I crack. Good? So look how much I need to calculate MA, M crack, I gross, I crack. Then I will be able to find this one, then I will put everything together. MA is the maximum surface load moments on the beam. Surface loads are total surface load WA equal 1.75, right? It means MA equal 1.75 times 24 square over 8.
126.
126 kib foot. Keep it in kib foot because it's moment over moment. So I gross, when you have the term I gross here, okay, it means ignore the steel in your cross section. So I gross equal BH cube over 12 equal 11 times 16 cube over 12. H cube, not D cube.
That's 3,754.
So let me put it here. I gross equal 3,754 and it's inch to the power 4. Okay? What's left is M crack and I crack. M crack and I crack. Okay? And we know we know that FR, the modulus of rupture, equal M cracking. Approximately, I'm going to assume I gross. I'm going to assume I gross. M crack. I can solve it without that. I can transform the section and show you how we do that. That's absolutely fine with me. It may take some calculation. Let me do it so you guys don't say how we did it or approximation. So FR from the ACI equals 7.5 square root F prime C. This number is
530.
530
Yeah.
PSI. So FR equal 530 PSI. Good? Now, the section will look like that just before cracking. Just before cracking. On both sides, we have N minus 1 AS from both sides. And this is 11. And this is 16. So I need to locate where is the neutral axis for this one, then I calculate the moment. Okay? And N when you have, it's N equal 29,000 divided by EC, which is 30. So N equal 7?
7.2.
So almost 7. Approximately 7. 7.2, approximately 7. So 7 minus 1 is 6 times AS. What's the area of steel we have in there? 3.16, right?
Yep.
So 3.16 times 6.
18.96.
18.96. This is this multiplication. Okay, N times AS. Now, Y bar from top equal the concrete area, which is 11 times 16 times 8, plus this area 18.96 times the distance from its neutral axis to the reference bar, which is 14, which is D, right? Divided by sum of the areas, 11 times 16 plus 18.96. So you will find your Y bar equal 11 times 16 times 8.
8.6.
8.6, which makes sense now, right? We expect the neutral axis of the composite section, once you have steel from the bottom, to be shifted more than 8, which is this is what we have in here, 8.6. That's our Y bar. Now we can calculate, so Y bar here equal 8.6 inch. Now we can calculate the amount of inertia of each of those components, or for the composite section. It will be, so IUT equal this one, 11 times 16 cube over 12 plus the area times the difference in this. So it's 11 times 16 times the difference between the two neutral axes, which is 8.6 minus 8. So it's 0.6 square. 0.6 square plus the component coming from the steel is AD square. So the area is 18.96 times D. Sorry, D. The D will be D minus 8.6 square. So it's 14 minus 8.6 square. You do this, you get IUT
43370
inch to the power 4. Look at I gross. This is way bigger than 1000 more than or like 800 more than this, or 600. So there is benefit to the steel. Okay? Sometimes you can approximate that. If you think you will have no problem with the deflection, you can approximate. Use I gross because it's smaller. The actual I is bigger. I'm gonna go back and write this later on. But I need more space here. Okay, guys? What's left now is I'm cracking. So I'm cracking equal IUT FR over the distance H minus Y bar. That's the distance from the neutral axis to the tension face. So that's that number, 4370 times 530 divided by 16 minus 8.6. All of that you divide by 12. You divide that, because this is in PSI and this is in inches, you divide by 12,000 to get it in kip foot. You expect a small number.
26.08.
26 kip foot. That's our I'm cracking. 26 kip foot. What's left in that equation I just show you is I cracking. That's what's left. Now let me show you how we calculate I crack. I will keep this for a moment. How the section will look like for I crack. It's the KD, remember? When crack, it go up to, this distance here will be KD. And this is the width of the section. So that's your neutral axis. And the steel here at the bottom become NAS. NAS. And we said 7, you can use N7, or if you want to use the exact value, that's fine now. So 7 times 3.16, that's your NAS. And the distance from here to here is D minus KD. So K, I'll show you how we get K. There's an equation, we derived it, it depends on N and rho. And we have N, we have rho. But the values are listed for you. Here, in table A6 in the appendix. Okay, this is the formula for K. This is the formula for K. Equals square root of 2 rho n plus rho n square minus rho n outside the square root. And this is J if you want. So our n is 7, almost 7. Here. And rho is 0.021. 0.02, almost 0.02. Almost 0.02. So K is 0.4. K is 0.407. K is 0.407. Or calculate it from the formula. So KD is what now? It's 0.407 times 14, which is 0.407. K guys, just for you to clarify it, it's 0.407.
So KD it's 5.7.
5.7 inch. So this distance is 5.7. If this is 5.7, 14 minus 5.7 is 8.13. Right? Now look, what's I for this? It's 1/3 B this cube plus this area times the distance from here to here square. So I crack equal 1/3 times B, which is 11 inch, times 5.7 cube plus this 7 times 3.16, that's A times D square, which is 8.3 square. I say D square, this is the parallel axis theorem, not the D that we are using. AD square.
So that's 2202.
2202 inch to the power 4. Look at this now, for you to just to notice. So I crack, when the section crack, the moment of inertia or the inertia decrease by from 4,370, that's the actual we have, the transform, to this 2202. What's the ratio between them? Half. So almost 0.5. I told you it's 0.4, 0.45, 0.5. Okay, it decreased by half. That's the stiffness or the moment of inertia. So we have everything now to start our calculation for IEffective. And you may be observing something in a minute. So again, IEffective equal. M cracking is what? 26. Divided by M A is 126. Cube times I what? I gross. 3754. Plus 1 minus this thing. Times I cracking, which is this. This will give you I effective. It's a weighted average. This is like a factor. M crack over M A is a factor. Cubed. Look, the smaller the value here, the smaller this thing here. And the bigger this. Because if this is a small number here, when you cube it, when you multiply by itself 3 times, become very small number. So it's basically it's taking almost nothing from this. All what it's taking is this.
So it's 2215.
It's funny, right? Is there any difference between I effective and I crack? Is it even worth it? Calculating IUT and all of that thing. So sometimes, to be honest, if you want to be conservative and it's very close approximation, take I effective equal I crack. Don't calculate I effective, it's allowed by the code. But I effective, for sure, it's higher than I crack. So if you took I crack, you are on the safe side. You are on the safe side. Now if you took I crack and you still did not find any problem with the deflection, move on. If you find a problem that can be fixed if I is little bit higher, go back and calculate the actual I. Okay? But if it work with you with I crack, that's it. Because you know I effective is slightly more than I crack. Good? That's just to show you they are really close. Most of my calculation and my examples, as I solve over the years, they are almost close. Sometimes this is little bit bigger, but close. Especially when you have this ratio bigger. When M cracking is big compared with MA. Now we are ready to calculate the deflection. We said delta now 5W L4 over 384 EI. That's an easy, just straightforward, just plug in numbers. However, you just need to pay attention to the units. Look, I'm going to calculate the live load, delta live load. Equal 5 times, how much the live load? The service loads, always when you calculate the deflection, you calculate for service load. It's 0.75. What units? Okay, per foot. I'm going to do something here. Just give me 1 second. Times. What's L? 24. So change to inch. 24 foot times 12 inch. This is all after I do the change to the power 4. Divided by 384. E is E for concrete, which is 4030. It's in KSI. So everything is in inch and kept at KSI except this one here. I'm going to change it in a minute. Times I effective, the one we just calculated. So this is EC and this is I effective, which is 2215. And this is also an inch to the power 4. The only unit that is in kip per foot is W. So I need to change this one into kip per inch. So look what you do to change units. You remove the foot. How many inch is the foot? 12 inch. So you replace it with 12 inch. Now the unit is inch, but there is 12 inch. So you need to divide the 0.75 per 12. You divide the 0.75 per 12. That's why usually if you don't do this one, your calculations are off by 12. If you do that, how much you get? your delta
0.63.
equal 0.63 inch. And this makes sense. You're not gonna get like 6-inch deflection. You're not gonna get 0.006 something. Okay? 0.6 half-inch, something like that. Is this good or not? Is this good or not? So let's see what the ACI code says. If you go to that table, which is based on the ACI or copied from the ACI code, says for floors. So what we have is a floor beam. A beam that's part of a floor. Says this table here. Say not supporting or attached to non-structural elements likely to be damaged by large deflections. That's most of the time is the case. That the floor is not supporting any elements. That's if the deflection of a deflection of 0.6 inch will break, or like glass windows, all of these things that's sensitive. Typically we don't have this issue. Says immediate deflection due to live load must be less or equal L over 360. ACI code limit, this must be less than or equal L over 360. And L over 360 is?
That will be 0.8.
That's 24 times 12 over 360 equal 0.8 inch.
Yep.
So we have delta live load equal 0.63 inch. It is less than or equal 0.8 inch. So the section is good. So the section is good. The deflection is fine. So guys, look, I know some of you, when you're seeing a design project in some places, you try to make sure your beams are fine with the deflection, so you don't have to check the deflection. So you keep squeezing or increasing the floor thickness, all of that. You don't have to. It doesn't mean that the deflection is bad. It means the deflection needs to be checked. Like some softwares will give you like a red flag on the deflection. Check the deflection due to live load. And there is another check on the long-term deflection, which is usually we don't check it. Or we can check it, no problem about it. It's so easy. I mean, you just need to calculate the dead load deflection. You need to know how much of the live load is sustained. Then there is a lambda delta factor based on how many years or how many months the live load will be sustained. But this is the most important item that need to be checked, the live load deflection. And as I keep repeating, the dead load deflection is usually controlled. Okay? There's one more thing I want to show you, which is part of the next topic, which is the development length or the cutoff points. Look. So how many bars we needed? We needed for number 8, right? We needed for number 8. Where do we need them? Here, at the maximum moment. It's maximum. This is positive moment. At the maximum moment location, which was 173 kip foot, that's how much we needed. Now the question is, where is the location at which to number 8 will be enough? See the question? You don't have to continue the 4 all the way, because the moment as you approach the support is 0. So at what location you can stop 2 of them? At what location you can stop 2 of them? It's like you have the following. So that's your beam. You have 4 bars. 2 all the way. This is the center line. And 2 will go up to a distance here. Then they can be stopped. So 2 bars. And those 2 number 8. They are at the same level. They are at the same level. I'm just drawing them this way for you guys so you can see them. But where do we stop them? What's this distance from here to here? We call it the cutoff point. We call it the cutoff point. Theoretical cutoff point. So how we check this thing? We no longer need 2 bars when the strength provided by 2 bars is enough. So what's the strength provided by 2 bars? Easy. The area of 2 number 8 will give you how much area of steel? It is on the table. It's 3.16 divided by 2.
1.58.
So that's 1.58 inches square. What's phi mn? Equal. Phi for sure will be 0.9 because for number 8 it was 0.9 times 1.58 times Fy 60 times D, which is 14, minus A over 2. And what's A? AS times Fy over 0.85 times F prime C, which is 5, times B, which is 11. You get A from here.
That's 2.03.
2 inch. If that's 2, what's 3 mn?
Um, 1109. But that's wait.
Once you do this, like this is 13 times 60, 13 times 60 times 1.58 times 0.9 divided by 12.
That's 92.5.
So that's 92.5 kip foot. So when the moment is 92.5 kip foot, I just need 2 bars. Right? 2 bars will be enough. Here, this is the calculation. The strength of 2 bars will give you 92.5. So from your structural analysis, from the moment diagram, if you can tell where is the location of the moment, so this is the moment diagram, how it looks like. So this is the loading. This is W ultimate. How much W ultimate now? It was 1.2 times 1 plus 1.6 times 0.75.
2.4.
2.4, did we use 2.4? Per foot, right? And this length is 24 foot. So the moment diagram again will look like the following. It's positive parabola, and this is the maximum here is the one we calculated, 172.8 kip foot. So I'm looking for a moment here. When this moment is 92.5, from here to here, we just need 2 bars. Within this region, we need 4 bars. From here to here, and from here to the support, we need 2 bars only. So it's not similar triangles. You need to find the location where the moment become that much. So what's the reaction here? It's W ultimate times 24 divided by 2, or W ultimate 2.4 times 12.
That's 28.8.
This is 28.8 kip. So you don't know what is that location, you're looking for it. So you take a cut at distance x to find x. So your cut will look like this. That's your reaction. And this is your loading, 2.4. And this distance x you're looking for. This is the distance when the moment become 92.5. So your moment is how much? 92.5. Why I'm drawing this one? Because it's a positive moment. Now everything you need to know what's the shear here. You care less about the shear. Take the moment at this point equal to 0. Sum the moment at x equal to 0 to find x. You will find that, don't forget this by the way, 2.4 kip per foot. Okay? So the moment here will be, this gives this, 92.5, that's positive. If I take counterclockwise, positive. minus 28.8 times x. That's clockwise. Then this 2.4 is positive, plus 2.4 times x, that's the resultant. Its location from this point is x squared. So 2.4 x squared over 2 equal to 0. If you do this, solve this equation, you will get x equal
3.82.
3.82 foot.
Yeah.
Foot. From the left end, by the way, there's two values. You'll find two values.
Yeah, the other one.
The other one will be this one.
It's 20.18.
20.18, which is 24 minus that will give you 3.82. So you found this and this. So one of them is enough. So you know from each support, at 3.82 from each support, you just need 2 bars. Within the middle, you need that much. But look now. So now we know what's the theoretical cut-off points. And this is what I'm going to cover in the following lecture. So we said the following. Let's summarize. So that's the middle of the bar. So again, 2 bars will go all the way. This is the cover from here, it's 2 inch. And we have 2 bars at the same level, I'm just showing you so for demonstration. Okay? This distance is 12. And this is 12 foot. So we said from here to here, how much do I don't no longer need? 3.8? 3.82, 3.82, right? So if I have 3.82, 12 minus that number,
that's 8.18.
so this 8.18 foot. 8.18. Now look, the code says, I'm going to explain this in the next lecture. The code says when you no longer need them, that's the theoretical cut-off point, you cannot stop it there. There's something called extension 1. Add this extension, typically 12 inch or 8 dB. 8 times the diameter of the bar or 12 inch. So basically you will have to extend 12 inch from here or 8 dB. Which is, let's say if our diameter is 1 inch, so that's plus 8 inch here. Now look, from that distance to this location here, this length must be greater than the development length. And I'm going to explain later on why is that. So that length must provide enough development length for the bars to develop their Fy in the middle. In the next lecture, I'm going to explain everything about the development length, and you're going to understand why that thing. But now you know how to calculate the cutoff points, when we can terminate some bars, stop 2 of them, stop 1 of them, and all of that. And see you then. Thank you, Gerard.